Okay, so we will continue with scheduling metrics. So we define turnaround time as time completion of the process minus the time it arrived or the time arrival. Because we have assumed that all jobs arrive at the same time, for now, time arrival will be equal to 0, and hence turnaround is equals to time completion. This fact will change as we relax the aforementioned assumptions. You should note that turnaround time is a performance metric, which will be our primary focus in this chapter. Another metric of interest is fairness, as measured, for example, by Jeans Fairness Index. So, a turnaround time is a performance metric, meaning how fast the process was executed. So, or time completion. Another is fairness. So, performance and fairness are often at odds in scheduling. A scheduler, for example, may optimize performance but at the cost of preventing a few jobs from running, thus decreasing fairness. This conundrum shows that life isn't always perfect. So performance and fairness, you cannot have both, as with Pareto principle, in which only few things could consume 80% of the resources. So if you're doing that, therefore you are not serving all the resources. So it's the same principle with this scheduling metric. So first in, first out. Since this is the first algorithm that we will gonna tackle to see if there it can be applied to our operating system. So just like data structure and algorithm, we will also see that algorithm for our operating system, the right algorithm for our operating system scheduler are different for different scenarios depending on our goals. Let's do a quick example together. Imagine 3 jobs arrive in the systems A, B, and C at roughly the same time. Time arrival equals 0. Because FIFO has to put some job first, let's assume that they all arrive simultaneously. A arrived just a hair before B, which arrived just hair before C. Assume also that each job runs for 10 seconds. What will the average turnaround time be for these jobs? So here's the graph. FIFO simple example. Figure 7.1. You can see that A finishes at 10, B at 20, and C at 30. Thus, the average turnaround time for the 3 jobs is simply 10 plus 20 plus 30 over 3 equals to 20. Computing turnaround time is as easy as that. Presumably, you figured this out by now. But just in case, let's do an example to show how jobs of different lengths can lead to trouble for FIFO scheduling. So in particular, let's again assume 3 jobs, A, B, and C, but this time A runs for 100 seconds while B and C run for 10 each. Figure 7.2, why FIFO is not that great. As you can see in figure 7.2, job A runs first for the full 100 seconds before B or C even get a chance to run. Thus, the average turnaround time for the system is high, a painful 110 seconds. So 100 plus 110 plus 120 over 3 equals to 110. So this FIFO is not good for turnaround time. So the problem is generally referred to as the convoy effect, where a number of relatively short potential consumers of a resource get queued behind a heavyweight resource consumer. This scheduling scenario might remind you of a single line at a grocery store and what you feel like when you see the person in front of you with 3 carts full of provisions and checkbook out. It's going to be a while. Tip: the principle of SJF. Shortest job first represents a general scheduling principle that can be applied to any system, where the perceived turnaround time per customer, or in our case, a job, matters. Think of any line you have waited in. If the establishment in question cares about customer satisfaction, it is likely they have taken SJF into account. For example, grocery stores commonly have a 10 times or less line to ensure that shoppers with only a few things to purchase don't get stuck behind the family preparing for some upcoming nuclear winter. So, this principle of SJF represents a general scheduling principle that can be applied to any system, even in operating system. So here, shortest job first. Let's take example, but with SJF as our scheduling policy. Figure 17.3 shows the result of running A, B, and C. Hopefully, the diagram makes it clear why SJF performs much better with regards to average turnaround time. Simply by running B and C before A, SJF reduces average turnaround time from 110 seconds to 50, more than a factor of 2 improvement. So since we've started with the shortest job, we are able to minimize the turnaround time of the jobs, because the turnaround time is the average of how long each job took. So here we started with the shortest job, which allows us to do that. So aside preemptive schedulers, in the old days of batch computing, a number of non-preemptive job schedulers were developed. Such systems would run each job to completion before considering whether to run a new job. Virtually all modern schedulers are preemptive and quite willing to stop one process from running in order to run another. So most of modern operating system is actually preemptive, which means that it allows you to stop one job and run another. Now, we will gonna discuss different algorithm or scheduler for our operating system. So some are better for Windows, or some are used by Windows, some are used by Linux. But as we will see, they could have a little bit different implementation or a completely different implementation. It really depends on their goal. This implies that the scheduler employs the mechanisms we learned about previously. In particular, the scheduler can perform a context switch, stopping one running process temporarily and resuming or starting another. So the context switch we have discussed, in which the interrupt implicitly save the register and the program counter from the kernel per process stock, and then return from trap, trigger the return from trap handler, and then the OS handle that trap, and then the OS save the register and the stack pointer to its process structure, and then it points the stack pointer to the new or the register of process B. So it points that to the actual hardware in its kernel stack, which allows the processor, or to the OS and processor, to context switch between A and B. So this is how modern operating system works. That's why we're able to use different processes at the same time, stopping one running process temporarily and resuming or starting another. In fact, given our assumption about jobs all arriving at the same time, we could prove that SJF is indeed an optimal scheduling algorithm. So because we have an assumption that the arrival is first 0, these are the best algorithm. since with our optimistic assumption. But however, we will gonna relax that assumption because it's an optimistic assumption. We will gonna relax that as we move, such as defining other arrival time as well, not just 0. However, you are in a system class, not theory of operations research. No proofs are allowed. Thus, we arrive upon a good approach to scheduling with SJF. But our assumptions are still fairly unrealistic. Let's relax another. In particular, we can target assumption 2 and now assume that jobs can arrive at any time instead of all at once. So instead of 0 at arrival time, let's tweak it a bit in which it arrives in different time. What problem does this lead to? Here, we can illustrate the problem again with an example. This time, assume A arrives at t equals to 0 and needs to run for 100 seconds. Whereas B and C arrive at t equals to 10 and each need to run for 10 seconds. With pure SJF, we get scheduled seen in figure 7.4. So you can see here, A arrives at 0 times 0 and needs to run for 100 seconds until 100, and B and C arrive at t equals to 10 and run for 10 seconds. So as you can see, they have this nice SJF with late arrivals from B and C. As you can see from the figure, even though B and C arrives shortly after A, they are still forced to wait until A has completed and thus suffer the same convoy problem. Average turnaround time for these 3 jobs is 103.33. What can a scheduler can do? So from 50 seconds, it became 103.33 when we relax the algorithm a little bit. Now here is how we resolve that. A shortest time to complete first STCF algorithm. To address this concern, we need to relax assumption 3. That job must run to completion. So let's do that. So this is how we switch context, because we don't need the job to complete. We also need some machinery within the scheduler itself. As you might have guessed, given our previous discussion about timer interrupts and context switching, the scheduler can certainly do something else when 8 and C arrive. It can preempt job A and decide to run another job. Again, as you might have guessed, given our previous discussion about timer interrupts and context switching, the scheduler can certainly do something else when B and C arrive. It can preempt job. So this is where the context switching came. So the scheduler could choose to run the other process while the process are still on the queue. So because there is longer processes that needs more time, therefore we could choose to run those in a late priority, which we will gonna discuss, and decide to run another job, perhaps continuing A later. SJF, by our definition, is a non-preemptive scheduler because it needs to complete the process and thus suffers from the problem described above. Fortunately, there is a scheduler which does exactly that, add preemptive to SJF, that allows you to context switch. It doesn't need you to complete the process. It allows you to switch while the process is still working. So that's STCF, or preemptive shortest job first PSJF scheduler. Anytime a new job enters the system, the STCF scheduler determines which of the remaining jobs, including the new job, has the least time left. and schedule that one. Anytime a new job enters the system, the STCF scheduler determines which of the remaining jobs, including the new job, has the least time left and schedule that one. So this actually does not use priority yet. It scheduled the least amount of process or the time to completion process first so that it complete first. Thus, in our example, so that it could reduce the turnaround time. In our example, STCF would preempt A and run B and C to completion, since that will gonna be completed first. Only when they are finished would A's remaining time to be scheduled. Figure 7.5 shows an example. STCF simple example. The result is a much improved average turnaround time, 50 seconds. So here, as you can see, 120 minus 0 plus 20 minus 10 plus 30 minus 10 over 3. So that's 50 seconds turnaround time since we preempt it. And as before, given our new assumptions, STF is probably optimal given that SJF is optimal if all jobs arrive at the same time. You should probably be able to see the intuition behind the optimality of STCF. So as you can see, the response time here is improved, or the turnaround time is improved to 50 seconds. So why is that? Because we start with 120 minus 0 and then plus 20 minus 10. So here 20 minus 10 plus 30 minus 10 because it only says 10. So a new metric response time. Thus, if we knew job lengths and that jobs only use the CPU and our only metric was turnaround time, the STCF would be a great policy. So if we already know the length of the job or its time completion, and our only the metric that's important to us is a turnaround time, then STCF algorithm would be a great scheduler policy. Remember, the OS use this policy to know what to run in these jobs, while the hardware use the mechanism such as the context switching and then hardware interrupts and trap handler to switch process. Now, in fact, for a number of early batch computing systems, these types of scheduling algorithm made some sense. However, the introduction of time-shared machines changed all of that. Now users would sit at terminal and demand interactive performance from the system as well. So this used to be the algorithm for OS, but as things became more interactive, the user demands more, and thus a new metric was born, which is response time. We define response time as the time from when the job arrives in a system to the first time it is scheduled. So from the time it arrived to the first time it is scheduled. So it's kind of like when you type in a keyboard, you must see something immediately, usually less than a second to make the system responsive. So T response equals to time first RAM minus time arrival. Some defined it slightly differently, like to also include the time until the job produce some kind of response. So some define it slightly differently, like to also include the time until the job produces some kind of response. So some actually define this differently, to also include the time until the job produce some kind of response. So the actual time that the job produced response. Our definition is the best case version of this. Essentially assuming that job produce produces a response instantaneously. So we assume that the job respond instantaneously. Uh, so we only calculate the first run and minus its arrival. So here's an example as GF again. So bad for response time because you wait for the process to complete round robin. Figure 7 is 7.7. Good for response time. For example, if we had a schedule from figure 7.5 with A arriving at time 0 and B and C at time 10, the response time of each job is as follows: 0 for job A, 0 for B, and 10 for C. Average 3.33 seconds. As you might be thinking, STCF and related disciplines are not particularly good for response time. So, because of the need for interactive, this algorithm was disposed because it's not good for response time. If 3 jobs arrive at the same time, for example, the third job has to wait for the previous 2 jobs to run in their entirety before being scheduled just once. So again, if 3 jobs arrive at the same time, for example, the third job has to wait for the previous 2 jobs to run in their entirety before being scheduled just once. So even if they arrive at the same time, the third job needs to wait for the other 2 jobs to run. While great for turnaround time, this approach is quite bad for response time and interactivity. Indeed, imagine a string at a terminal typing and having to wait 10 seconds to see a response from the system. So let's say you have type keyboard and then wait for the keyboard to be typed 10 seconds after, just because some other job get scheduled in front of you. Not too pleasant. There comes round robin. So to solve this problem, we will introduce a new scheduling algorithm, classically referred to as round robin or round robin scheduling. So the basic idea is simple. Instead of running jobs to completion, RR runs a job at a time. Runs a job for a time slice, sometimes called a scheduling quantum, and then switches to the next job in the run queue. So this is how we improve the response time. This is how we utilize the context switch mechanism provided to us by hardware and the OS. It repeatedly does so until the jobs are finished. For this reason, RR is sometimes called time slicing. Note that the length of a time slice must be a multiple of the time interrupt period. Note that the length of a time slice must be a multiple of time interrupt period. So the length of this time slice that round robin does should be a multiply of the time interrupt period. So the time interrupt period is determined from your trap table, the one you created from interrupt handler. Thus, if the timer interrupts every 10 milliseconds, the time slice could be 10, 20, or any other multiple of 10s. So since the timer interrupts is every 10 milliseconds, the value of the time slice that this algorithm does, or the number of scheduling quantum, should be a multiple of 10 milliseconds, such as 10, 20, 30, and then it switches to the next job in the run queue, and then it repeatedly do so until the job are finished. So tip: amortization can reduce cost. The general technique of amortization is commonly used in systems when there is a fixed cost to some operation. By incurring that cost less often, by performing the operation fewer times, the total cost to the system is reduced. Again, the general technique of amortization is commonly used in systems when there is a fixed cost to some operations. By incurring that cost less often, by performing the operation fewer times, the total cost to the system is reduced. So, by performing those high cost operation fewer times, the total cost to the system is reduced. That is what we call amortization when there is a fixed cost to some operation. For example, if the time slice is set to 10 milliseconds and the context switch cost is 1 ms, roughly 10% of the time is spent context switching and is thus wasted. If we want to amortize this cost, we can increase the time slice like to 100 ms. Instead of 10 ms. In this case, less than 1% of the time is spent context switching, and thus the cost of time slicing has been amortized. So, relevant to this round robin, since we constantly move between processes, is the concept of amortization. So, instead of wasting this 10% context switching from 10 milliseconds, and we know that the context switch cost is 1 ms, which is roughly 10% of time is spent in context switching, we can instead lower it down to 1% by making the time slice 100 ms. So in this case, less than 1% of time is spent context switching, which saves us a lot of time. So to understand RR in more detail, let's look at example. Assume 3 jobs A, B, and C arrive at the same time in the system and that they each wish to run for 5 seconds. An SJF scheduler ran each job to completion before running another. In contrast, RR, with a time slice of 1 second, would cycle through the jobs quickly. So the time slice of this is 1 second. So here, the 100 milliseconds is, I think it's roughly 1 second. Just a moment. So 100 milliseconds is actually equal to 0.1 seconds. But in this case, an SJF scheduler ran its job to completion. In contrast, the RR with the time slice of 1 second would cycle through the jobs quickly every second. So here's an example for that. Here's an SJF, bad for response time, round robin, good for response time because we cycle through it every second. We cycle through the process. So the average response time of RR is 0 plus 1 plus 2 over 3 equals to 1 only 1 second. For SJF, average response time is 0 plus 5 plus 10 equals to 5 seconds. As you can see, the length of the time slice is critical for RR. The shorter it is, the better performance of RR under the response time metric. So, the length of that time slice actually determines its response time. So, as you can see, a 1 second time slice made the response time 1 second. However, making the time slice too short is problematic. Suddenly, the cost of context switching will dominate overall performance. So, that cause context switching, for example, you have a process that generally or naturally takes longer and you stop it, you stop the momentum, right? Thus, deciding on the length of the time slice presents a trade-off to a system designer, making it long enough to amortize the cost of switching without making it so long that the system is no longer responsive. So, making it long so that you complete the process that does not reduce the turnaround time as much, and balancing that with your response time is a key process in designing this system using round robin. Note that the cost of context switching does not arise solely from the OS actions of saving and restoring a few registers, just like what we've discussed in the previous video. When program runs, they build up great deal of state in CPU caches. TLBs, branch predictions, and other on-chip hardware. So when you run the process, the build up great deal of state in CPU caches, TLBs, branch predictors, and other on-chip hardware, or the implicit saving in what we did in context switching. We will discuss more of this TLBs and memory, virtualizing memory in virtualizing memory chapter. Switching to another job causes this state to be flash and new state relevant to the currently running job to be brought in. So that previous state will be flash if you always context switch, which remember that's how we revert back to the previous state of the process, which may exact a noticeable performance cost since we need to start the state of the process again. RR with a reasonable time slice is then an excellent scheduler if response time is our only metric. But what about our old friend turnaround time? Let's look at our example again. A, B, and C, each with running times of 5 seconds, arrive at the same time, and RR is the scheduler with a long 1 second time slice. We can see from the picture above that A finishes at 13, B at 14, and C at 15, for an average of 14. Pretty awful. It is not surprising then that RR is indeed one of the worst policies if turnaround time is our metric. Intuitively, this should make sense. What RR is doing is stretching out each job as long as it can by only running each job for a short time before moving to the next, because turnaround time only cares about when job finish. RR is nearly pessimal, even worse than simple FIFO in many cases. So these are actually worse in FIFO, which is the first algorithm we've discussed when it comes to turnaround time, because it chops the process, so it takes longer for the process to complete. So what if that process needs to be complete faster? So more generally, any policy such that RR that is fair, i.e. that evenly divides the CPU among active processes on a small time scale, will perform poorly on metrics such as turnaround time. Again, more generally, any policy such as RR that is fair, like that evenly divides the CPU among active processes on a small time scale, that evenly divides the CPU among active processes. So a policy such as RR that evenly divides the CPU, or use the context switch we've discussed earlier, among active processes on a small time scale, will perform poorly on metrics such as turnaround time. Indeed, this is an inherent trade-off. If you are willing to be unfair, you can run shorter jobs to completion, but at the cost of response time. If you instead value fairness, response time is lowered, but at the cost of turnaround time. This type of trade-off is common in systems. You can have your cake and eat it too. Tip: overlap enables higher utilization. When possible, overlap operations to maximize the utilization of systems. Overlap is useful in many different domains, including when performing disk I/O or sending messages to remote machines. Like when one process is doing I/O, you can then choose to run the CPU on another process while the other process is running I/O. In either case, starting the operation and then switching to other work is a good idea. In either case, starting the operation and then switching to other work is a good idea and improves the overall utilization and efficiency of the system. Again, starting the operation and then switching to other work is a good idea while it's doing I/O. So this is how overlap enables higher utilization of CPU and improves the overall utilization and efficiency of the system. Overall, we're discussing the details on how multiprogramming actually utilizes the CPU while it's doing I/O, which is one of the more prevalent innovation in operating system we discussed in its history. Now, incorporating our I/O, first, we will relax assumption 4. Of course, all programs perform I/O. Imagine a program that didn't take any input. It would produce the same output each time. A scheduler clearly has a decision to make when a job initiates an I/O request, because the currently running job won't be using the CPU during the I/O. It's block waiting for I/O completion. If the I/O is sent to a hard disk drive, the process might be blocked for a few milliseconds or longer, depending on the current I/O load of the drive. Thus, the scheduler should probably schedule another job on the CPU at that time. The scheduler also has to make decision when I/O completes. When that occurs, an interrupt is raised. So the scheduler also are the one making the decision when the I/O completes. And then when that I/O occurs, it triggers, or an interrupt will be raised, and the OS runs and move the process that issued the I/O. So as you can see, along this context switching, let's say an I/O is completed on something, it actually interrupt that process using our interrupt timer. So the scheduler trigger that, so that that I/O complete process is stopped, so that it can revert back to its process. So, and the OS runs and moves the process that issued the I/O from block back to ready state. To understand this issue better, let's assume we have two jobs, A and B, which each need 50 milliseconds of CPU time. However, there's one obvious difference. A runs for 10 ms and then issues an I/O request. So both are 50 ms, but after A, first subjob, which is 10 ms, it issues an I/O request, which will then be interrupted by the interrupter using the scheduler algorithm. Assume here that I/Os each take 10 milliseconds, whereas B simply uses the CPU for 50 ms and performs no I/O. So here's the graph for that. So the scheduler runs A first, then B after. So you can see A run for 10 milliseconds, and then it run I/O for 10 ms, then run 10 ms again, 10 ms, 10 ms, 10 ms, 10 ms, 10 ms, and then it completes, while B just used the CPU all throughout. Assume you are trying to build a STCF scheduler, which is the improvement of SJF, which allow for preemptive or switching of tasks. How should such a scheduler account for the fact that A is broken up into 5 10 ms subjobs, whereas B is just a single 50 ms CPU demand? Clearly, just running one job and then other without considering how to take I/O into account makes little sense. So we will now be more strict on our assumption, and we will relax that assumption now. A common approach is to treat each 10 ms subjob of A, which I mentioned. So we treat that as a subjob instead of the part of a job. Thus, when the system starts, its choice is whether to schedule a 10 ms A or a 50 ms B. With STCF, the choice is clear. Choose the shorter one, in this case A. And then when the first job, so with STCF, we actually apply this here. With I/O, we choose the A and then B, and then alternate between them. Then, when the first subjob of A has completed, only B is left, and it begins running. Then, a new subjob A is submitted, and it preempts B and run for 10 ms. Again, it preempts this using the interrupt handler set up in the trap table, and it is done by the scheduler depending on the algorithm you use. Doing so allows for overlap, with the CPU being used by one process while waiting for the I/O of another process to complete. The system is thus better utilized. Here, an overlap allows better use of resources. And thus, we see how a scheduler might incorporate I/O by treating each CPU burst as a job. So these are one of the common tricks that we could use based on our analysis of these different algorithms. We could treat each CPU burst as a job. The scheduler makes sure processes that are interactive get run frequently. So this scheduler, one of the ideas we get from here is that we run this as a sub-job. So the scheduler treat that to make the response time of SCTF more interactive. While those interactive jobs are performing I/O, other CPU intensive jobs run, thus better utilizing the processor. So as you can see in this case, when we include the I/O and then we treat that as a subjob using the same algorithm SCTF, we are able to somehow get the gist or the idea on how to tackle these processes more efficiently. And thus we see how scheduler might incorporate I/O by treating each CPU burst as a job. The scheduler makes sure processes that are interactive get run frequently. No more Oracle. With the basic approach to I/O in place, we come to our final assumption that the scheduler knows the length of each job. As we said before, this is likely the worst assumption we could make. In fact, in general purpose OS like the ones we care about, the OS usually knows very little about the length of each job. Thus, how can we build an approach that behaves like SJF/STCF without such a priori knowledge? Further, how can we incorporate some of the ideas we have seen with the RR scheduler so that response time is also quite good? So the question now is, the last assumption we took is that we know how long the process will take, but most process is unpredictable because it's a program and it runs on different times. So how can we create an algorithm that allows us to predict all those processes, which is the magic of the scheduler, right? So how can we incorporate the algorithm, the good side of the SJTF or STCF algorithm and RR algorithm when it comes to turnaround and response time? So that's the question we're gonna answer in the next topic. We have introduced the basic ideas behind scheduling and developed two families of approaches. The first runs the shortest job remaining and thus optimizes turnaround time. The second alternates between all jobs and thus optimizes response time. Both are bad where the other is good. Alas, an inherent trade-off common in systems. We have also seen how might incorporate I/O into the picture, but have still not solved the problem of the fundamental inability of the OS to see into the future. Shortly, we will see how to overcome this problem by building a scheduler that uses the recent past to predict the future. This scheduler is known as the multi-level feedback queue, and it's the topic of the next chapter, scheduling. The multi-level feedback queue. In this chapter, we'll tackle the problem of developing one of the most well-known approaches to scheduling, known as the multi-level feedback queue or MLFQ. The multi-level feedback queue scheduler was first described by Corbato in 1962 in a system known as the Compatible Time Sharing System, CTESS, and this work, along with later work on Multics, led the ACM to award Corbato its highest honor, the Turing Award. The scheduler has subsequently been refined throughout the years to the implementation you will encounter in some modern systems. The fundamental problem MLFQ tries to address is twofold. First, it would like to optimize turnaround time, which, as we saw in the previous note, is done by running shorter job first. Unfortunately, the OS doesn't generally know how long a job will run for, exactly the knowledge that algorithms like SJF or STCF require. Second, MLFQ would like to make a system feel responsive to interactive users, like users sitting and staring at their screen waiting for a process to finish, and thus minimize response time. So you don't want to do nothing while your process are downloading. You want a response time, a fast response time that allows you to context switch as well to move to other jobs. Unfortunately, algorithms like round robin reduces response time but are terrible for turnaround time. Tip: learn from history. The multi-level feedback queue is an excellent example of a system that learns from the past to predict the future. Such approaches are common in operating system and many other places in computer science, including hardware branch predictors and caching algorithms. So the branch predictors and caching algorithms that we identified while context switching using round robin that may remove that previous state of the process is one of the things that this multi-level feedback queue solve. So these are actually are being used to those in computer science with those branch predictors and caching concept. Such approaches, such as those with an RR examples earlier, such approaches work when jobs have phases of behaviors. So these systems are particularly useful when when jobs or that processes have phases of behavior and thus predictable. So the phases of behavior we have is the context switch, right? How do we switch from one process to another? Therefore, we're gonna use how the previous history of the process. For example, some process take too long, therefore we will gonna put their priority at the lowest, while the shortest job, which needs to be completed faster, will be at a higher priority. But some process take too long at some point in time, but run faster in some point of time. So how do we create an algorithm for that? So that's where the multi-level feedback queue came. Such approaches work when jobs have pieces of their and thus predictable. Of course, one must be careful with such techniques as they can be easily be wrong and drive a system to make worse decision than they would with no knowledge at all. MLFQ basic rules. In our treatment, the MLFQ has a number of distinct queues, each assigned a different priority level. So to apply this algorithm, we will create a concept called distinct queues, which assign a different priority level. At any given time, a job that is ready to run is on a single queue. So a job that is ready to run is on a single queue. MLFQ uses priorities to decide which job should run at a given time. A job with a higher priority, like job on a higher queue, is chosen to run. Of course, more than one job may be on a given queue and thus have the same priority. In this case, we will just use round robin scheduling among those jobs. So these are one of the pseudocode or fundamental properties it must satisfy. So the if priority A is greater than priority B, A runs, B doesn't. So as it arrives on this algorithm, as the process arrives, it is first become a priority. Now what if both have the same priority? Then we do the context switch. We do the RR to implement them. Now the key to MLFU scheduling therefore lies in how the scheduler sets priorities. Rather than giving a fixed priority to each job, MLFQ varies the priority of a job based on its observed behavior. So the key or the main thing about or the main differentiator of MLFQ lies in the scheduler sets priorities. because the priority queue. Rather than giving a fixed priority to each job, MLFQ varies the priority of a job based on its observed behavior. If, for example, a job repeatedly relinquishes the CPU while waiting for input from the keyboard, MLFQ will keep its priority high. So if a job repeatedly relinquishes the CPU while waiting for input from the keyboard, it will keep its priority high, as this is how an interactive process may behave. If instead a job uses the CPU intensively for long periods of time, MLFQ will reduce its priority. So in other words, a job that uses the CPU intensively compared to job that uses CPU non-intensively, those jobs must be priority. Why? Because it completes faster and it requires interactivity, such as input from the keyboard. Remember round robin in the graph context switch, but it has a fast turnaround time. That's the same characteristic of the short processes as well. If instead job uses the CPU intensively for long periods of time, MLFQ will reduce its priority. In this way, MLFQ will try to learn about processes as they run. So, if the MLFQ learned that there is a job that runs intensively, it will reduce its priority as new process comes, and it will try to learn about processes as they run, and thus use the history of the job to predict its future behavior. So this is how it used the history and predict the future behavior. If you were to put forth a picture of what queues might look like at a given instant, we might see something like the following in figure 8.1 page 3. In this figure, two jobs A and B are the highest priority level. Therefore, we're gonna do a round robin or context switch from them, while job C is in the middle and job D is at the lowest priority. Given our current knowledge of how MLFQ works, the scheduler would just alternate time slices between A and B because they are the highest priority jobs in the system. So the scheduler would just process this first in round robin or context switch because they are the highest priority jobs in the system. Poor jobs C and D would never ever get to run an outrage. Of course, just showing a static snapshot of some queues does not really give you an idea of how MLFQ works. Of course, just showing a static snapshot of these queues does not give you. What you need is to understand how priority changes over time. So what makes complicated on this algorithm we have discussed, that's why they are not properly able to handle the edge cases, is because we're not discussing how the processes change over time. Some process took the CPU longer at some point in time, while in other times took the CPU in shorter bursts because it needs to be interactive, therefore needs to use a round robin. So attempt number 1, how to change the priority. We now must decide how MLFQ is going to change the priority level of a job, and thus which queue it is on over the lifetime of a job. So we now must decide how MLFQ is going to change the priority level of a job, and thus which queue it is on over the lifetime of a job. So we need to create some pseudocode or rules that will dictate how this scheduler change the priority level over the lifetime of a job. To do this, we must keep in mind our workload, a mix of interactive jobs that are short running. So that is our basis of this creating of algorithm. We are trying to handle a mix of interactive jobs which called workload that are short running and may frequently relinquish the CPU, and some longer running CPU bound jobs that need a lot of CPU time but where response time isn't important. For this, we need a new concept which we'll call the jobs allotment. This allotment is the amount of time a job can spend at a given priority level. So Again, the allotment is amount of time a job can spend at a given priority level. So these are the new concept that has been opened because of this new algorithm, which is not available, or the vocabulary that is opened in this algorithm, which is not available in the previous algorithm. So this allotment is amount of time that a job can spend at a given priority level before the scheduler reduces its priority. For simplicity, at first we will assume the allotment is equal to a single time slice. Here is our first attempt at a priority adjustment algorithm. So rule 1, if priority A is greater than priority B, A runs, B doesn't. Rule 2, if priority A is equals to priority B, A and B run in RR. Rule 3, when a job enters the system, it plays at the highest priority, the topmost queue. Again, rule 3, when a job enters the system, it is placed at the highest priority, the topmost queue. Rule 4a, if a job uses up its allotment while running, its priority is reduced, i.e. it moves down one queue. Rule 4b, if a job gives up the CPU, for example by performing an I/O operation before the allotment is up, it stays the same in priority level. So here's the graph. Figure 8.2, long-running job over time. Example 1, a single long-running job. So let's look at some example. First, we'll look at what happens when there has been a long-running job in the system with a time slice of 10 ms and with allotment set equal to the time slice. So again, first we will gonna assume that the allotment is equal to the time slice. Figure 8.2 shows what happened to this job over time in a 3-queue scheduler. So it's a 3-queue scheduler. Here's the least priority and here's the top priority. As you can see in the example, the job enters at the highest priority Q2. After a single time slice of 10 ms, the scheduler reduced the job priority by 1 and thus the job is on Q1. After running at Q1 for a time slice, the job is finally lowered to the lowest priority in the system, Q0, where it remains. Pretty simple? No. Example 2. Along came a short job. Now let's look at more complicated examples and hopefully see how MLFQ tries to approximate SJF. So this is how it approximates the shortest job first, which is the algorithm we have earlier. In this example, there are two jobs. A, which is long-running CPU intensive job, and B, which is a short-running interactive jobs. Assume A has been running for some time and then B arrives. What will happen? Will MLFQ approximate SJF for B? So here, figure 8.3 on page 5 left plots the results of this scenario. Job A shown in block. So as you can see, then it runs and then it moves downward and then it's completed. And then the A continue. Job A shown in block is running along in the lowest priority queue, as would any long-running CPU intensive jobs. B shown in gray arrives at time t equals to 100. So this arrived in t equal 100. One of the things that is differ from the previous algorithm examples we have and the assumptions we have before is this time arrival is different, which is 100 seconds, and thus is inserted into the highest queue as it runs time is short, only 20 ms. B completes before reaching the bottom queue. Since the runtime or the total completion is just 20 milliseconds, after the second byte or time slice, it completed. So in 2 time slices, then A resumes running at low priority. So from this example, you can hopefully understand one of the major goals of the algorithm, because it doesn't know whether a job will be a short job or a long-running job. It first assumes it might be a short job. So because it doesn't know if it is gonna be a short or long-running job. It made an intelligent assumption, kind of like in about face, where we assume we didn't notice, or we know the difference between probability and possibility. So since we know that if it's not a shortest job, we can always treat that as a longer job. We are able to make an intelligent guess, thus giving the job high priority. If it actually is just a short job, it will run quickly and complete it, right? So based on what we know of the characteristics of the process, which is once we run, it as a short job, and then if it goes to the second queue, if it's complete, therefore it will vanish. So it is not a longer job. If it's not a short job, it will slowly move down the queues and thus soon prove itself to be a long-running, more batch-like process. In this manner, MLFQ approximates SJF. So that's the magic of this scheduler. Again, first keyword is a priority queue. Second keyword is allotment using a time slice. And then third, what's the third? It assumed a short job. Actually, it's a sentence. So example 3, what about I/O? Let's look at example when some I/O, as rule 4b states above. If a process gives up the processor before using up its allotment, we can keep it at the same priority level. So if the processor, let's say it arrive and give up the processor and then use an I/O, we will keep its priority level. The intent of this rule is simple. If an interactive job, for example, is doing a lot of I/O, say by waiting for user input from the keyboard or mouse, it will relinquish the CPU before its allotment is complete. In such case, we don't wish to penalize the job and thus simply keep it at the same level. In figure 8.3, right, shows an example of how this works. So here, when an interactive job B shown in gray that needs the CPU only for 1 ms before performing an I/O, competing for the CPU with a long-running batch job A. So we are able to maintain the interactivity of B because we are able to keep its priority level. Thus, MLFQ approach keeps the B at the highest priority because it keeps releasing the CPU. If B is an interactive job, MLFQ further achieves its goal of running interactive jobs quickly. Problems with our current MLFQ. Now we thus have a basic MLFQ. It seemed to do a fairly good job sharing the CPU fairly between long-running jobs and letting short or I/O interactive jobs run quickly. Unfortunately, the approach we have developed thus far contains serious flaws. Can you think of any? First, there is the problem of starvation. If there are too many interactive jobs in the system, they will combine to consume all CPU time. And thus, long-running jobs will never receive any CPU time. They starve. So this actually have a problem. Because if there are too many interactive jobs in the system, they will combine to consume all CPU time. And these longer running pesos won't get their stage on the floor. We'd like to make some progress on these jobs even in this scenario. So these long running jobs is still important. Second, a smart user could rewrite their program to game the scheduler. Gaming the scheduler refers to the idea of doing something sneaky to trick the scheduler into giving you more than your fair share of resource. The algorithm we have described is susceptible to the following attack. Before the allotment is used, issued an I/O operation like to a file and thus relinquish the CPU. Doing so allows you to remain in the same queue or in the same priority and thus gain a higher percentage of CPU time. When done right, like by running for 99% of the allotment before relinquishing the CPU. So when done right, by running for 99% of the allotment before relinquishing the CPU, a job could nearly monopolize the CPU. Finally, a program may change its behavior over time. What was CPU bound may transition to a phase of interactivity. With our current approach, such job would be out of luck and not be treated like other interactive jobs in the system. So because of this algorithm we created, it's susceptible for gaming or some processes monopolizing the CPU. And this is what I'm saying. Some CPU bound may transition to a phase of interactivity on other times. So with our current approach, such a job would be out of luck and not be treated like other interactive jobs in the system. Tip: scheduling must be secure from attack. You might think that a scheduling policy, whether inside the OS itself, as discussed herein, or sorry, before that, since I've discussed that scheduling must be done right? Because if not, it will do more harm than good. So this is one of the things that or edge cases that we want to avoid here. Therefore, that for those rules that we have that will keep the priority while doing I/O is actually not the right one, which we're gonna replace later. Secondly, a smart user could tip: scheduling must be secure from attack. You might think that a scheduling policy, whether inside the OS itself, as discussed herein, or in a broader context, like in a distributed storage system I/O request handling, is not a security concern. But in increasingly many cases, it is exactly that. Again, you may think that scheduling policy, whether inside the OS itself, as discussed herein, or in a broader context, like in a distributed storage system I/O request handling, is not a security concern, but in increasingly many cases, it is exactly that. It's actually a security concern. Consider the modern data center, in which users from around the world share CPUs, memories, network, and storage systems without care in policy design and enforcement. So, the modern data center, which share the CPU, memory, and network without care of policy design and enforcement, it actually being run by an OS as well. So without enforcement or good policy design, a single user may be able to adversely harm others and gain advantage for itself. Thus, scheduling policy forms an important part of the security of a system and should be carefully constructed. The priority boost. The simple idea here is to periodically boost the priority of all the jobs in the system. So to solve that, monopolizing the CPU is to have a time. So this is the key. Another keyword for this as well. Periodically boost. So aside from assuming the first arrival as the shorter process, and then next would be to periodically boost the priority of all the jobs in the system so that everyone can have its fair share. There are many ways to achieve this, but let's just do some. The simple: throw them all in the topmost queue. Hence a new rule, Rule 5. After some time period S, move all the jobs in the system to the topmost queue. So after some time or S, such as 1 second, move all the jobs into the priority queue. Our new rule solves two problems at once. First, processes are guaranteed not to start by sitting in the top queue. A job will share the CPU with other higher priority jobs in a round-robin fashion. So by sitting in a top queue, a job will share CPU with other high priority in a round-robin fashion. So it will context switch between those processes and thus eventually receive service. Second, if a CPU-bound job has become interactive, the scheduler treats it properly once it has received the priority boost. Second, if a CPU-bound job has become interactive, the scheduler treats it properly once it has received the priority boost. So if it goes to the top priority and it switched to the phase of interactivity, it will be given its fair share. So let's see an example of this scenario. In this scenario, we just show the behavior of a long-running job when competing for the CPU with two short-running interactive jobs. Two graphs are shown, figure 8.4, page 7. On the left, there is no priority boost, and thus, the long-running job gets starved once the two short jobs arrive. On the right, there's a priority boost every 100 milliseconds, which is likely too small of a value, but used here for the example. As you can see, when this long-running job switched to phase of interactivity, it is able to get its fair share of the CPU with the B and C process. And thus, we at least guarantee that long-running job will make some progress, getting boosted to the higher priority every 100 milliseconds, and thus getting to run periodically. Of course, the addition of the time period S leads to the obvious question: what should S be set to? John Osterhout, a well-regarded system researcher, used to call such value in systems voodoo constants. So that's actually called voodoo constants. What time should you periodically run it in priority? Because they seem to require some form of black magic to set them correctly. Unfortunately, has that flavor. If it's set too high, long-running jobs could starve. Too low, and interactive jobs may not get proper share of the CPU. As such, it often left to the system administrator to find the right value. So this is a voodoo constant code, is because some change on this actually could determine or could make the system fail drastically. Or in the modern world, increasingly to automatic methods based on machine learning. So it could be set by system administrator, or modernly using a machine learning that learns from the past, right? Attempt number 3, better accounting. We now have one more problem to solve: how to prevent gaming our schedule. The real culprit here, as you might have guessed, are rules 4A and 4B, which let a job retain its priority by relinquishing the CPU before its allotment expires. So before its allotment expires, it lets to be in the same priority while it is doing the I/O. This is the real culprit, or the real blind spot with our algorithm. So what should we do? The solution here is to perform better accounting of CPU time as each level of the MLFQ. Instead of forgetting how much of its allotment a process used at a given level when it performs I/O, the scheduler should keep track once a process has used its allotment. So if it uses its allotment, it doesn't revert to 0. Or if it get its fair share of the CPU, the system or the scheduler must remember that even if that is just a small part of the pie that it was given to it, and it is demoted to the next priority queue immediately instead of keeping it at priority. So whether it uses its allotment in one long burst or many small ones should not matter. We thus rewrite Rule 4A and 4B to the following single rule. Rule 4. Once job uses up its small allotment at a given level, regardless of how many times it has given up the CPU, its priority reduced. It moved down one queue. So here's an example: 8.5 without left and with right gaming tolerance. So as you can see here, it didn't use that rule, therefore it monopolized the CPU, and this process, which is A, didn't get its fair share. But in here, as you can see, even it's just a little, it moves down of the queue because it needs to give up its fair share, right? And as it moves down, as you can see, the A, the long-running process, still have its fair share and therefore are able to utilize the CPU and not be monopolized by the short-running process. So tip: avoid voodoo constant, Osterhout's laws. Avoiding voodoo constant is a good idea whenever possible. Unfortunately, as in the example above, It's often difficult. One could try to make the system learn a good value, but that too is not straightforward. The frequent result, a configuration file filled with default parameter values that assists an administrator. So one could try to make the system learn a good value, but that too is not straightforward. The frequent result, a configuration file filled with default parameter values. So a configuration file with the default parameter values that a seasoned administrator can tweak when something isn't quite working correctly. So the result of the frequent or the usual result is a configuration file with the default parameter values. And then it is being tweaked when something isn't working correctly. As you can imagine, these are often left unmodified and left as a default, and thus we are left to hope that the defaults work well in the field. This tip brought to you by our old OS professor John Ousterhout, and hence we call it Ousterhout's law. So let's look an example. So we should avoid that voodoo constant. Instead, let the default be as it is and only change if it's not working properly. Let's look at an example, figure 8.5. It shows, oh my god, why do I have, let's look at an example in figure 8.5. It shows what happens when a workload tries to game the scheduler with the old rules 4A and 4B on the left. So here, as well as the new anti-gaming rule without any protection from gaming. A process can issue an I/O before its allotment ends. So without any protection from gaming, a process can issue an I/O before its allotment ends, thus staying at the same priority level and dominating CPU time. With better accounting in place, right, regardless of the I/O behavior of the process, it slowly moves down the queue and thus cannot gain an unfair share of the CPU. So that's the last keyword, moving down the queue or changing the rule. So the key before that is what's the key before that? We have some voodoo constant or elapsed time where we periodically move up the queue of the long-running CPU. So those are the key in our MLFQ algorithm or scheduler. So tuning MLFQ and other issues. A few other issues arises with MLFQ scheduling. One big question is how to parameterize such a scheduler. For example, how many queues should there be? How big should the time slice be per queue? The allotment, how often the priority boosted in order to avoid starvation and account for changes in behavior. There are no easy answer to these questions, and thus only some experience with workloads and subsequent tuning of the scheduler will lead to a satisfactory balance. So to answer a question, how big the or how many queue should be, how big the time slice, the allotment, the priority, how often it's boosted, and how can we avoid starvation and changes in behavior. There's no easy questions answers to this, and only with again go back to the workload, the number of processes your system currently tackle, and the tuning of the number in the scheduler, whether it's the time slice or the number of queue or how often you boost the process is all on you. But when it's working, usually the default, right? When it's working, you should not avoid changing it. So if it's not going left, or if it's not, if something not doing terribly wrong, don't change it. For example, most MLFQ variant allow for varying time slice length across different queues. So some of MLFQ variants actually allow for varying time slice length across different queues. The high priority queues are usually given short time slices. They are comprised of interactive jobs. After all, the high priority queues are usually given short time sliceless. So a high priority queue given a short time slices, where the low priority queue has a large time slice. So that's one of the variant of MLFQ. They are comprised of interactive jobs after all, and thus quickly alternating between them makes sense. So the reason why those high priority has a lower time slice is because they are round robin, or they're a short process. So therefore, round robining on them makes sense, like 10 or fewer milliseconds. So the lower priority queues, in contrast, containing long-running jobs that are CPU bound, hence how longer time slices work well, like 100 milliseconds. So figure 8.6 shows an example in which two jobs run for 20 ms at the highest level queue with a 10 ms time slice, 40 ms in the middle, 20 ms time slice, and with a 40 ms time slice at the lowest. So this is how the time slices are divided each queue. So the Solaris MLFQ implementation, the time sharing schedule class or TS, is particularly easy to configure. So there's a variant, or the called Solaris MLFQ implementation. The time sharing scheduling class or TS, or time sharing, is particularly easy to configure when it comes to that. It provides a set of tables that determine exactly how a priority of a process is altered throughout its lifetime. So it provides a set of tables that determine exactly how the priority of a process is altered throughout its lifetime. Again, it provides a set of tables that determines how the priority is of a process is altered throughout its lifetime. So the key here is a table that determines the priority. Remember, we don't have set rules in determining the priority. Here in Solaris, they have a table that determine exactly how the priority of a process is altered throughout its lifetime, how long each time slice is, and how often to boost the priority of a job. And the table also have the value on how often should you boost and how each time is sliced. So an administrator can map with this table in order to make the scheduler behave in different ways. Default values of the table are 60 queues. So this is the default value, 60 queues, with slowly increasing time slice lengths from 20 milliseconds, highest priority, to a few hundred milliseconds, lowest, and priorities boosted around every 1 second or so. So those are the values to remember. 20 milliseconds with the highest priority, increasing to a few hundred milliseconds until to the lowest priority, which is the 60th queue, and are boosted around every 1 second. So other MLFQ schedulers don't use a table or the exact rules described in this chapter. So other MLFQ don't necessarily use the exact algorithm we created or the table that Solaris have. Rather, they adjust priorities using mathematical formulas. So some variant of MLFQ adjust priorities using mathematical formula. For example, the FreeBSD schedule version 4.3 uses a formula to calculate the current priority level of a job. So it uses a formula to calculate the priority level, or to determine its priority queue, basing it on how much CPU the process has used. So it based on how much CPU it used. In addition, usage is decayed over time, providing the desired priority boost in a different manner than described herein. See EPEMA's paper for an excellent overview of such decay usage algorithm and their properties. So aside from calculating it using a math formula for priority level, a usage is decayed over time is also one of their measurement, how the usage is decayed over time. So those are algorithm they use as well. Of course, it uses the history to act on the future. So finally, many scheduler have a few other features that you might encounter. For example, some schedulers reserve the highest priority levels for operating system work. So some of the scheduler actually reserve that highest priority for operating system. It's still an MLFQ. Thus, typical user jobs can never obtain the highest levels of priority in the system. Some systems also allow user advice to help set priorities. So some have this command line that allows you as a user to determine what command or what processes are in the highest priority. For example, by using the command line utility nice, you can increase or decrease the priority of a job somewhat and thus increase or decrease its chances of running at any given time. See the man pages for more. Tip: use advice where possible. As the operating system rarely knows what is best for each and every process of the system, it is often useful to provide interfaces to allow users or administrator to provide some hints to the OS. So these are one of the good practices, is to allow this onto your scheduler, an advice command or interface where the user determine which processes are run in the highest priority. We often call such hints advice, as the OS need not necessarily pay attention to it, but rather might take the advice into account in order to make a better decision. So those are actually called hints, which not necessarily followed by the OS, because some of that could be a security risk, but it takes that into account to produce better decisions. Such hints are useful in many parts of the OS, including the scheduler, like with NICE, memory manager, MadVice, and the file system, inform prefetching and caching. So it's useful for prefetching and caching. That's why it is taken by the a good practice of an OS is to ask for hint for the user on how it prioritize its queue, because it also highly useful for file system and memory manager, not just the OS scheduler. So we have described a scheduling approach known as the multi-level feedback queue. Hopefully you can now see why it's called that. It has multiple levels of queues. So again, that's the key. It's the multiple levels of queues for the priority queue, and uses feedback to determine if the priority of a given to determine the priority of a given job. Also, it makes an intelligent assumption that the process that arrive will run shortly unless proven otherwise. History, its guide. Pay attention to how jobs behave over time and treat them accordingly. The refined set of MLFQ rules spread throughout the chapter are reproduced here for your viewing pleasure. Rule 1: if priority A is greater than priority V, A runs, B doesn't. Rule 2: if priority A is equals to priority B, A and B run in context switching, like round robin, using time slice, quantum length of the given queue. So depending on the time slice given to that priority queue, number will be in context switch using round robin algorithm. When a job enters the system, so as you can see, another useful insight here is round robin algorithm is part of the MLFQ. So rule 3: when a job enters the system, it is placed at the highest priority, the topmost queue. Rule 4: once a job uses up its allotment at a given level, regardless of how many times it has given up the CPU, its priority is reduced. So whether it given up or get the time slice for just a little bit, it needs to move down in priority queue rather than keeping its priority when it's doing an IO or other non-CPU task job. Rule 5: after some time period, S move all the jobs in the system to the topmost queue to boost all the jobs. So MLFQ is interesting for the following reason. Instead of demanding a priori knowledge of the nature of a job, it observes the execution of a job and prioritize it accordingly. So instead of demanding a priori knowledge of the nature of a job, it observes the execution of the job and prioritizes it accordingly. So this answer the question, how do we create an algorithm that predicts the time completion or the ramp time? So the answer is we don't. We observe the execution and prioritize it accordingly. We create intelligent assumption, and we create a queue concept and then a time slice concept depending on the workload we have. Also, we also determine each edge cases that we must satisfy depending on the current limitation of the system, such as running a boost to avoid gaming the system, and then after some time, period S, move all the jobs to the topmost queue. So MLFQ is interesting for the following reason. Instead of demanding of a prior knowledge of nature of a job, it observes the execution of job and prioritize it accordingly. In this way, it manages to achieve the best of both worlds. It can deliver excellent overall performance similar to SJF/STCF for short-running interactive jobs, and it's fair and makes progress for long-running CPU-intensive workloads. For this reason, many systems including BSD Unix derivatives, Solaris, and Windows NT, and subsequent Windows operating system use a form of MLFQ as their base scheduler.